Okay, so today we're going to be deriving an expression for the density of a log that is a perfect cylinder. And it's going to be sitting above at a water level, not moving. And with that is going to have a height h, and the log is we're going to say is going to have a radius r. So I'm just going to draw a picture for this. Pen was not working. Okay, so we have our log in the water, and the radius is going to be r. And the water level is going to be at some height, and we're going to call that height h. And then we're going to draw the rest of the log. And we're just going to call the the length of the log L. So what do we have in this problem? We have a log, and we know that it's sitting in water and it's floating, so we know that the density of the log, rho, has to be less than the density of the water. And we also know that there's no acceleration, so our acceleration is 0. So we're not going to have one, when we add up our forces, we're not going to have one force going in the other direction more than the other because the acceleration is 0. And speaking of forces, in this case we have a buoyant force. And this buoyant force is the weight of the fluid displaced, and weight is equal to the mass times the acceleration due to gravity. So since this system is not accelerating, we can say that the mass of the water times the gravity, g, is equal to the mass of the log times g. And then we can cancel out the g's. So we can say the mass of the water is equal to the mass of the log. And the mass of the water can also be written as the density of the water. So the density of the water times the cross-sectional area, so we'll just call this AC, of the water, of the fluid below the water level. So it'll be this space right here. So I'm going to just draw a picture so we can kind of show what area we're talking about. So the water level is this right here, I just selected, and this will be the area we want for it under there. And then times the length of the water. And then we can say this is also equal to the density of the log times the cross-sectional area of the whole log. And in this case, because it's a circle, it's going to be pi r squared. And then times the length of the log. And we can see that we have two L's on both sides, so we can cancel those out. So now we have our expression relating the density of the water with the density of the log. And what we're going to want to do next is we just need to figure out how to find this cross-sectional area of the under the water level. So we can go ahead and do that next. But what we're going to want to do is we can say, kind of just like split it up real quick, and we can say that the water level, the cross-sectional area of the water level right under the water level, we can say that is equal to the area of the whole circle minus the area of this section above the water level. And we can say this section above the water level, we can say that's equal to the area of the sector of a circle, like just a part of a section from the circle with this arc, and we minus the triangular area of the triangle. And then, so if we find the area of this sector and the area of the triangle, we can just subtract the full area of the circle, and we can use that to get the cross-sectional area of this guy right here, in which we're going to put back into our equation to solve for the density of the log. So I'm going to go ahead and draw the picture again, just so we can see it a little better. I'll zoom out a little bit here, and we're going to just have the log right here, and we'll have the water level. H is right here, and then we're going to draw our radius right here, and then we're going to draw another radius so we can kind of make a section of the circle. Oh, that's a bad line. So we make a section of the circle that we want to find, and then I'm also going to write in this other our height of our triangle, because this will help us calculate the area of it. After we calculate the area of the sector. So we're going to call this h minus, little h minus r, and that will be this guy right here, this height of this triangle that we just drew of a section. So first we need to find this guy, this area of the sector, and what we're going to do is we're going to need to compare this section we have with the rest of this circle on the area of the circle. So we're going to we're just going to define an angle right there, and we're going to call these two angles, we're just going to go ahead and call them theta. And we can multiply this theta by the full area of the circle, and then we can go ahead and divide by the number of radians in a circle. And this will help us isolate for theta. So since there's two of them, we're going to have 2 theta, and then we're going to have that divided by 2 pi, the radians in the circle, and then times pi r squared. So we know that pi's are going to cancel, 2's are going to cancel, so that just leaves us with the area of this section right here. That leaves us with it being theta r squared. And we don't really have a definition for theta. We only know that we only know our h and r. So what we're going to need to do is kind of use this our picture to determine what theta is. So if you can see from the picture, you can see that the height is h minus r, and you can see that we have a radius over here, r, and our theta is right here. So what we can do is use the inverse cos and our adjacent over our hypotenuse to determine what theta is in terms of h and r. So we're going to go ahead and do that. So we're going to just say theta is equal to inverse cos of the adjacent h minus r over the hypotenuse r, and then we can put that back into this equation. So we know that our area of our circle, or of our section of our circle, is going to be equal to the negative cosine, the inverse cosine, sorry, of h minus r over r times r squared. So we're going to go ahead and save this for later, and when we next need to do is find the area of the triangle, and then we're going to take the area of the triangle and subtract it from the area of this, and that will help us get one step closer to getting to our density expression. So I'm going to zoom out again a little bit, and we're going to scroll down. So now what we need to do is, how are we going to find the area of our triangle? So I don't have to keep scrolling back up and down. I'm just going to go ahead and draw another circle with our picture. So we have a radius r, and then we have our water level, height, h minus r. And what we don't have is, I didn't draw the picture very well, but we don't have are these bases right here. You know what, I'm actually going to redraw this picture just so I can explain it a little bit better. Radius, height, r, h minus r. Okay, so what we don't have is this base right here and this base right here. So what we're just going to go ahead and call those x. We're just going to call them x. And we're going to use those bases to solve for our area of the triangle. So you can see we have our triangle right here in this section right here. So the definition of area of a triangle is 1/2 times the base times the height. So we have a equals 1/2 base height, and we can say that this is equal to 1/2 our bases being x. So this of one of these triangles. So we have 2 of them right here. We're just going to say this will be the area for one of the triangles. So we'll have 1/2 x, the base, times the height, and the height in this case is h minus r. And now what we're going to want to do is we need to solve for x. We don't know what x is. But if we use our triangle again, kind of what we did with theta, we can figure out what x is. So when you have, I'm going to go ahead and just draw the triangle by itself over here. You have x, you have r, and you have your h minus r right here. So you can see that our hypotenuse is r. And you can use kind of like the Pythagorean theorem. So you can write r squared. You can set that equal to the 2 sides of the triangle squared. So you can have r squared equals x squared plus h minus r squared. But no, we need to solve for x. So now we just need to solve for x, and to do that we're going to have x squared equals r squared minus h minus r squared. And we can square both sides, and that will end up giving us x equals the square root this will give us x equals the square root of 2rh minus h squared. And actually I messed up. This is supposed to be r minus h because r is bigger than h. So this is actually supposed to be r minus h. I got confused a little bit, so this will be r minus h over r. And we're good. So this will also be r minus h over r. So it's actually r minus h, not h minus r. I messed up there because our radius is bigger than our height. So our radius would be first. But anyways, so we have solved for our x. X is equal to 2rh minus h squared, because you can see that when you distribute the negative, the r squareds will cancel, and you will end up with a positive 2rh minus a h squared, because the negative distributes. So now we can just go ahead and plug this x right back into our equation up here for our area of the triangle. So we have our area of triangle equals 1/2 times the square root 2rh minus h squared times r minus h. So if we go back to the pictures I drew, we know that the cross-sectional area we want is this shape. Right now, we just have determined the triangle and the area of the sector. And these two areas, if we subtract them, will equal this area, in which we can get from the total area of the circle minus this section above the water level where the log's sticking out. And that's what we have just found when we subtract the area of the sector minus the area of the triangle. So now we're going to do that. So our area of the sector we had, if we scroll back up here, we know that the area of the circular sector was the negative cos r squared times the negative cos of r minus h over r. And then, so we have the area of this, we can just go ahead and subtract the area of the triangle. But we do have two of these triangles right here, so we do need to multiply this by 2. And when you do that, the 1/2 and the 2 will cancel to just make 1. So we'll just have minus square root of 2rh minus h squared times r minus h. And this will be our area of this guy right here, above the water level. This will be the area of that. And the last step we need to do is we just need to subtract pi r squared from this area. So we're going to have pi r squared, don't know why I said pi squared r, pi r squared minus, and we're going to have parentheses, r squared cosine of the inverse cosine of r minus h over r minus square root of 2rh minus h squared times r minus h, and then close with the one more parentheses. So this will be our cross-sectional area of this piece right here, and this is the part of the log that sticks up above the water level. So now what we need to do is, when we subtract pi r squared from this entire equation, this will give us our cross-sectional area under the water level in which we are trying to find. Now we just plug this into our equation that related to densities. So we have our density of water times our area of this, which is right here, and then this was equal to the density of the log times the area of, or the cross-sectional area of the log, which is pi r squared. And we know that our density of water is equal to 1,000 kilograms per meters cubed. So we can go ahead and isolate for the log density of the log. So the density of the log is equal to 1,000 times the cross-sectional area under the water level, which is this right here. We have pi r squared minus r squared cosine, inverse cosine of r minus h over r minus square root of 2rh minus h squared times r minus h. And we can divide all of this by the density of, or the cross-sectional area of the log, which was just a full circle pi r squared. So we divide this all by pi r squared, and we are done. This equation, or this expression, will give us the density of a log sitting in water, and we are assuming that this log is not moving at all, and that the log is also a perfect cylinder, and it has a maximum height h above the water level and a radius r. So thank you for watching, and have a great day.